Good afternoon. My name is Stephanie. As you can see, we have a few spectra analysis to determine a molecule. Right. So the formula that we have is C6H12O2. We're going to be using each one of these to determine our actual molecule. First, we're going to start with determining our degree of saturation, which is the formula used at the top. In the analysis of a molecule formula of organic molecules, degree of saturation is a calculation that determines the number of rings or pi bonds. The degree of saturation is also known as the index of hydrogen deficiency, double bond equivalent, or unsaturated index. As you can see, our formula up here, we did 2C plus 2 plus N minus X minus H divided by 2. And actually filled in, we have 2 times 6 plus 2 minus 12 divided by 2, which ends up 2 divided by 2, or 1, which means we either have a double bond or a ring. I'm going to start with our first spectral analysis. So we're going to use our chart to determine where our molecule or pieces of our molecule are labeled. As you can see, at 174, we have a carbon double bond. Double bond to an oxygen and another oxygen. Right around 62, we have a carbon bond to an oxygen. And then right around 18, we have a carbon-carbon bond on our first spectra analysis. And we're going to go down to our IR spectra analysis. It's upside down, my apologies. Nope, it's upside down this time. Do it this way. Do the same thing to help determine what kind of molecule possibly be working with. As you can see, we have our C to an H right around 2950, most likely an alkyne. Right around 1750 of a C double bonded to an oxygen, which will be an ester group. And then right around 1190, 1200, we have a C bonded to an oxygen, and that's what that stretch is. You can see we can verify that using our chart. So C bonded to an oxygen with a stretch right around 11 to 15, depending on what it is. For our C double bonded to C bonded to an H, right around 29. We have one right there. And then our final portion of our analysis, we're going to use our chemical shift to determine how the molecule is put together. As you can see, we have, actually, let me start on the other side. As you can see, we have 2 hydrogens here, right about 4.2, 4 lines, which makes it a quartet. Would be an oxygen bonded to a CH2 and a CH3. I will show you my documentation momentarily. Next, you have a CH2, which is right around 2.3. It's got at least 3 defined lines. So triplet, most likely a CO bonded to a CH2 and then to a CH2, so part of the chain. We have another 2H right around 1.7. So you can see there's multiple lines itself there. Approximately 6, so that would give us a sextet. Should also be part of the structure itself, like the bond, the chained bond. So a CH3, CH2, CH2, and then CO. Our 3H right around 1.1, easily defined as a triplet. It's an oxygen bonded to a CH2 and a CH3. And then our final, our 3H, right around 0.9. It's a triplet as well. It's a CH3 bonded to a CH2, bonded to a CH2, bonded to a CO. So it gives us an idea of what we might be working with in terms of our actual molecule itself. Based off of all of our spectra analysis, this would be the proposed structure that we came up with, which is ethyl butyrate.